On January 2nd, 2026, updated tracking data showed that 3I Atlas shifted its trajectory by a fraction of a degree. The number was small, so small that early models almost ignored it. But in deep space, small changes don't survive. Natural objects don't hold precise deviations for long. They drift back. They smooth out. This one didn't. Across multiple observations taken days apart, the shift stayed nearly identical. That's not how random motion behaves. At first, the change was labeled as noise, a rounding error, a temporary artifact. However, when the next dataset arrived, the same deviation appeared again. Same direction, same scale. That's where it gets strange, because if this were a normal interstellar object, the change should have faded almost immediately. Instead, it stayed. And that single measurement is why 3I Atlas became very hard to ignore. Before this measurement, 3I Atlas already looked unusual. It entered the solar system fast, clean, on a trajectory that suggested it came from far beyond our local stellar neighborhood. Astronomers expected something simple. Gravity in, gravity out. No surprises. But the tracking data showed a consistent sideways deviation. Not a sudden jump. Not acceleration, a steady offset. Think of throwing a paper airplane in a calm room. If it slowly drifts left, you expect air currents, uneven folds, a wobble. But if the airplane moves left without wobbling, something else is happening. That's the problem scientists faced. The measurement didn't show chaos, it showed control-like stability. But there was no visible source, no gas jets, no dust plume, no fragmentation. However, the object also wasn't tumbling wildly. Its brightness stayed relatively stable. Its rotation didn't spike. That combination is rare because most small forces in space leave fingerprints. This one didn't. And once researchers realized the deviation wasn't fading, they stopped treating it as background noise. In interstellar space, objects behave in predictable ways. They are shaped by gravity, heat, momentum. If an object changes direction, there's usually a visible reason. For example, comets release gas as they warm. That gas acts like a weak engine. But 3I Atlas showed no classic comet behavior. No expanding cloud. No tail forming in expected wavelengths. That's the first issue. The second issue is timing. Even when outgassing happens, it changes over time. As the object rotates, the force shifts. The path becomes uneven, but this deviation stayed aligned. That's where existing models begin to struggle. Imagine a car rolling downhill with the engine off. If it slowly turns, you'd look for a slope, a curve, a push. If none exist, the turn doesn't make sense. However, scientists are careful. They don't jump to conclusions. Instead, they ask a simpler question. What natural explanation could produce a steady force without visible evidence? So far, none fit cleanly. And that's why the measurement matters. Not because it proves something extraordinary, but because it refuses to disappear. Scientists are approaching this cautiously. They are not asking, what is it? They are asking what could cause this behavior. Explanation 1. A subtle natural process. The safest explanation is that something is happening that current instruments can't fully resolve. Possibilities include extremely weak material release, surface properties that reflect heat unevenly, an unusual shape producing steady thermal forces. These are real effects. They've been observed before. But here's the problem. All these forces tend to change. As the object rotates, the force shifts. As it cools, the force weakens. But the measurement didn't weaken. It stayed consistent across multiple observations. That doesn't disprove a natural cause, but it makes it harder to model. Explanation 2. A rare interstellar object. Type. Another possibility is that 3i Atlas belongs to a class of objects we've barely seen. Interstellar space is ancient. Conditions there are extreme. Objects can form in environments we don't observe locally. That could produce behaviors that don't match expectations. However, rarity alone doesn't explain stability. Rare things can still behave unpredictably. This didn't. That's where the uncertainty grows. Not because the explanation is dramatic, but because it's incomplete. Scientists don't like incomplete explanations. They keep watching. Right now, the focus isn't speculation. It's monitoring. Upcoming observations will look for long-term trajectory drift, changes in brightness, subtle rotational shifts. If the deviation fades, the mystery likely ends. If it persists, models will need revision. That's the real outcome here, not a discovery, not a revelation, but a pressure point. Because science advances when measurements refuse to behave, and this one didn't. So the real question isn't on what is 3i Atlas, it's this. Why did this measurement stay when it shouldn't have? Subscribe to follow the next update, because the next data release may finally answer that question.